In this video, we're going to look at the dynamics of a particle moving in a straight line. To begin with, I want to consider the concept of a force acting on an object. A force is something that will make an object accelerate. In short, it causes a change in the motion of that object. The object, if we took for example a toy car and that was at rest on a surface, if we applied a force, it would start the vehicle up. If we had now, for example, a particle, and a particle was moving with a constant velocity or a constant speed, and I applied a force, it might increase or decrease the speed. The force may even bring the particle to rest. The vast majority of our work in this unit will focus on Newton's second law, F is equal to ma. Before we go ahead and look at Newton's second law, let's just first consider Newton's first law. Newton's first law of motion states that an object will remain at a constant speed or at rest, or if you like in equilibrium, unless acted upon by a resultant force. The cliche example given now is an ice hockey puck. An ice hockey puck should continue infinitely if it's now not acted on by anything else, because the surface it's on is so smooth and there's no resultant force acting upon it. In all reality, that's highly unlikely. A good example of Newton's first law would be a passenger in a car. So as you're travelling along in a car and you now have a force that stops that car, you will move forward relative to the car. So Newton's first law, essentially now the body, which we're going to have as a particle, will now remain at rest or a steady speed unless acted upon by a resultant force. Let's move on and look at Newton's second law. Newton's second law is quite famous. It's F is equal to ma. Force is equal to the mass multiplied by the acceleration. Or if you like, force is a product of mass and acceleration. Of course, if we've got a product of mass and acceleration, acceleration is a vector, therefore force is a vector quantity. It has both magnitude and direction. The unit of force is the Newton. So, the Newton, or if you like, a capital N. That's the force that will cause a mass of 1 kilogram to accelerate at 1 meter per second squared. Okay, what we want to do in this video is just look at a range of forces acting on what we call a particle. So when we're modelling these situations, we often have, for example, a car. If a car is on a 3-mile straight road, we would model the car as a particle. So its size relative to our bigger picture is very small. So we can put its centre of mass in one fixed point. So often you'll hear as a particle might be a parcel being pushed along the floor. It might be a book. All we're going to do is use a very simplistic model that takes that particle and looks at the forces acting on it. I want to start off with a concept that many people, and quite rightly, don't find intuitive. And I'm going to draw up now a basic, even this, we could just call this a floor. So this is going to be now the floor. I'm going to place a particle on there. So this is now what we'd have as a particle. Let's say now that we have a mass on here of m. So we've got the mass. If we consider the forces now, if this is just sitting on a flat surface, the flat surface is not buckling or breaking. If we consider the forces acting on this particular particle and the mass of the particle is m, we're going to have the weight acting downwards. Now the weight is mass times by gravity. Generally we take gravity to be 9.8 meters per second squared, and this here now is weight. So we say that the weight is mg newtons. If this was 5 kilograms, it would be 5g newtons. So we'd write now mg newtons. Now, what we're looking at here is the acceleration. This object, this particle, is not accelerating upwards. So for example, if I was standing in a room, I've not all of a sudden hurtled towards the ceiling. We can say that the resultant is going to be 0. There is no acceleration. So if I put 0 meters per second squared, in the same way, in the other way, I'm not accelerating downwards. And the reason that's the case is now there is a normal reaction force. Later on we'll look at equal and opposite forces, but essentially as I push down on the floor, the floor pushes back with an equal and an opposite force, and this is called the resultant force. And now I should say this is called the normal force, as the resultant here is going to be 0. I push down with my weight. My weight is going through the floor, and that now is mass times gravity, and in response here I will have a normal reaction force. So if we look at Newton's second law, F is equal to ma. In this case we can see the following. If I take now down to be the positive direction, I can look at the following. I can say that this is going to be mg. So I'm now what we call resolving downwards, and we'll look at the idea of resolving shortly. As I push down now, the normal reaction, which is perpendicular to this surface, is pushing back up. So I can say mg minus r will be equal to the mass times acceleration. So on the left hand side I've got the forces, and then on the right hand side I'm going to have now m multiplied by 0. So if you like, if you wanted to put this round, technically if we switch this round it will be slightly more accurate, as I'm now resolving in the direction of the acceleration. But as there's no acceleration, it doesn't really matter. So what we can see from here now is r will be equal to mg. The normal reaction force will be equal to the product of the mass times by gravity. So it's called normal as it's at a 90-degree right angle. Now if this wasn't the case and I started accelerating upwards, we could essentially say now that r minus mg is equal to whatever the acceleration is multiplied by the mass. It's highly unlikely, as when we're walking around we would start accelerating upwards. So this now is an example of the forces acting on the particle. So I've got my weight pushing down and I've got a normal reaction pushing back up. Okay, let's take this model again and we'll do now some forces acting in the horizontal plane. So what I'll have then, if I take the particle, if I put this on, when I model this up, I can see now that I'm going to have my weight acting down. I'm going to have my normal reaction. And normal, you've probably met the word normal before, it means perpendicular now. So we got this perpendicular. If I consider that there's no vertical acceleration, if we were resolving up and down, F equals ma, F would be equal to 0. There's no resultant force. When we say resolving, we're looking at solving basic equations to find the resultant force. We'll go on to resolving now horizontal and vertical components of force as we go, but essentially this is the idea. So when you're asked to resolve, the notation we might want to use in this particular case now is in the vertical direction. I could use this arrow to show that I'm resolving the force. There are lots of different ways that you could show this. You could say now resolving in this direction, or if you like, resolving now in the horizontal direction. Generally we resolve in the direction of the acceleration. So if we're now accelerating to the right, we would show that we're resolving to the right. Okay, let's go ahead now and apply a horizontal force. So let's have a look at this right here, and what we can do is define. So I'm going to put some information on and we're just going to model a basic situation. So this might now be, for example, this might be a toy, okay? And I've put a bit of string on it, and what I'm going to do is pull it along a smooth floor. Now when we talk about smooth, we talk about no friction between the particle, which we model up, and now the surface. In a later video we will look at the idea of friction. So we've either got now a smooth surface where there'll be no friction, or a rough surface where we do have a frictional force. Friction is a force that opposes the motion. For now we will just take this, and I will say that this is going to be a force, and I'm going to say that this is T. T now stands in this particular case for tension. Tension is a force that pulls. So if you can imagine now, I'm standing here with this rope pulling, and it's going to be parallel to the floor. So I'm just pulling in this direction. If I said now that the mass, let's say this was 5 kilograms, we would have now 5g newtons. So our weight acting down would be 5g newtons. G is 9.8 meters per second squared, so we could say now that this would be 5 lots of 9.8, which is going to be 49 newtons. We'd have our normal reaction force. That would now be perpendicular to what we would call the plane. Okay, I've now got tension in here, and what I'm going to say is that we're going to be accelerating in this direction right here, and let's say the acceleration is going to be 2 meters per second squared. What we're going to do is look at resolving the forces to find the value of T. So I might want to find the tension in this rope. So let's go ahead, and we would describe this as a smooth surface. So we don't need to consider any frictional force. If I did, I could model this up in the opposite direction. That would be a force opposing the motion, and we could put that on like so. And we'll look at a scenario of that, like that shortly. So what I can say is the following. I can use Newton's second law, force is equal to mass times acceleration. So if I now resolve in the direction of the acceleration, and that's the general idea, we're going to have the following. We've got T. That is now this tension I'm pulling now, and it's important that we see that this is parallel. If it's not parallel, and we'll look at an example of that shortly, we'll have to resolve the horizontal and vertical components of this force. But for now, it's parallel. So what we're going to have then, we've got no force opposing the motion. It's not as if someone else is the other side pulling it the other way. It's not as if there's a frictional force opposing this. We can say that T will be equal to the mass, which is 5, multiplied by the acceleration, which is 2. So we can see now F is equal to ma. I'm using Newton's second law. I'm now looking in the direction of motion. So we could say that the tension was going to be equal to 10, and that would be newtons, and that would be my answer. So nice and straightforward. So we would be asked to find the value of T given this particular case. Okay, let's look at another one. Let's go for something else. So let's say we've got this scenario. Now, in terms of your vertical acceleration, very rarely will you see in these basic models something telling you that the vertical acceleration is 0. You can consider now if you've got, and this might be, let's say that this is again a toy car. And what I do, I give this a kick now, and essentially it's now set in action, okay? And we've picked it up at the stage where it is in action, and it's just now in motion. It's going along. Now, if we consider the forces acting on this, we will have the weight acting down. Now, when we come to resolving, if we say that the vertical acceleration is 0, which is going to be quite clear, we don't have to consider these forces if we're just looking now at the horizontal motion, because this isn't jumping up and down the air, it's not going through the carpet, it's just as it is. I'm putting these on for completeness. So let's say we've got now this toy car, and let's say it's got a mass, okay? So the mass is going to be 2 kilograms. The weight acting down, weight is mass times gravity, so this would be 2g newtons, or if you like, 19.6 newtons. We'd have the normal reaction force, and we might be told now that this acceleration is 0 meters per second squared. This is just telling you that it's continuing along in this direction. So let's say this is going along, and it's on a carpet. What we might have is the following, okay? We might have a force, and this might be the frictional force. So on the carpet, there's going to be now some friction. This is going to oppose the motion. Now, if I put the acceleration in this direction, quite clearly, if I resolved this way, we would end up now with a negative acceleration, or if we like, a deceleration. So this can be shown either way. If we took this now to be the direction of motion, we could put the acceleration, we'll say let's go for -3 meters per second squared. So if I now resolved in this direction here, what we'd have going to the right, we'd have minus the frictional force, and that would be equal to the mass, which is 2, multiplied by the acceleration, which is going to be -3. So we can see now that the frictional force is going to be equal to 6. Minus F is equal to -6. So the frictional force will be equal to 6 newtons. So that's what we have. Nice and logical, fairly straightforward. And as stated in a later video, we will look at the idea of the frictional force and what the frictional force is and how we can do some more extensive work with that. Let's look at another scenario. Let's say we had the following. Let's say now I was pulling an object along the floor. So again, I'm going to pull this parallel to the surface. And then, for example, now somebody else was pulling in the opposite direction. And I was pulling in this direction now, and I had a 10 Newton force. Let's say that this is going to be, again, 2 kilograms. And let's say I don't know this force right here. So this I'm going to call T. So just picture this. I'm pulling in this direction. Someone is pulling in this direction now, but I'm still winning the battle. So we've got now an acceleration. And let's say the acceleration is going to be, let's say it's going to be 3 meters per second squared. I'm working with some really straightforward values now to essentially make this easy. So what we want to do is find the force that that person is pulling in the other direction with. So imagine this again to be some toy, 2 children pulling one way, pulling the other. So using Newton's second law, F is equal to ma. We will resolve now from left to right, okay? So we're going to have the force of 10 newtons pulling this way, minus now the force of the T in the opposite direction, and that would be equal to the mass, which is 2, multiplied by the acceleration. So we can see that 10 minus T will be equal to 6. We can see that 10 minus 6 will be equal to T. So we can see that T would be equal to 4 newtons. So the person pulling in the opposite direction, the tension in the rope that they're pulling is going to be 4 newtons. Later on we will look at modelling up ropes. Generally we see them to be light, inextensible strings. Light means that they add no mass to the particular model that we're doing. But that will be covered later on. Okay, so that's another example. We might have now a different type of force. We've looked now at a tension. We might have something called a thrust or thrust. Thrust is a pushing force. So tension is a pulling force and thrust might be a pushing force. So say I'm now in a warehouse and I'm pushing this box along the floor and I'm making it accelerate. It will be fairly slow, but let's say that this is going to be a box of 100 kilograms. So we've got a mass of 100 kilograms. I'm now putting some thrust in this. And again, I might want to call this T. We might have now this acceleration and it might be 1 meter per second squared. So we might want to find out the thrust. Now if we consider the thrust, we could say that now using Newton's second law, F is equal to ma. We could now resolve and we could say that T was equal to the mass, which is going to be 100, multiplied by the acceleration, which is 1. So T would be equal to 100 newtons. And that is what I'd have. Now we might have a frictional force opposing this motion. So say I had now some force, and again we will look at the force opposing the motion. So let's say now that we had this force right here and we had F, okay? In this particular case, when we modelled this up, this time we would have now T minus F is equal to the mass times acceleration. So I'm considering now the direction of these forces. So this would now be T minus F is equal to 100, and then we'd end up now with 1. What we'd need here is some more information to go ahead and solve if I hadn't done this bit. But we can see from here now that we've got T to be 100 in this part right here. In fact, let's change this up slightly. Let's say that I've got now, let's say I've got a thrust, and let's just change the model up to make this slightly easier to comprehend. Let's say I've got now a thrust, and let's say this is going to be now 15 newtons. So my thrust now, I'm pushing with 15 newtons. What we could say is 15 minus this frictional force, which is opposing the motion, will be equal to the mass, and we'll keep the acceleration at 1. We can see from this now that the frictional force in the model right here is going to be, if I add it to both sides, we're going to have F on this side, and we're going to have now minus 85. So this is telling me that I have an 85 Newton force opposing the motion. And the fact that it's negative essentially just means now that I'm resolving from left to right, therefore it's acting in the other direction. If this had been in the opposite direction, it would be positive, and quite clearly we would end up with a different scenario. But the frictional force is opposing the motion. So we would model this frictional force when we have now a rough surface. So rough surface friction will now act on the particle. If it's smooth, we simply leave it out of the model. Now, all of these forces we've looked at so far have been parallel or perpendicular to a plane. So we've modelled them up. It might be the case that we don't have that. So we might have a situation now where I have a particle and I have a force being applied at an angle. So if I now have this at an angle, and I like to put it here, certainly don't have to put it here, but we might now have a force. And that force, let's just spin this round, might be given to be at a certain angle. All we do now is resolve in terms of the horizontal and vertical components of this force. So if I said that this force now was here at an angle of 30 degrees, and we had now, for example, let's say that we called this force. Okay, now let's look at some other forces acting on this. Let's put a normal reaction and the weight. So here's my weight acting down, and we would have now the normal reaction force. Generally we call the normal reaction force R. So let's put the normal reaction force on here. Let's say this is R. Let's say we've got now a mass of 2, and this is going to be the weight acting down. So this is going to be 2g newtons. Let's now say that we've got, let's change the value of, let's go, in fact we'll leave this. No, we'll put a force on. Let's put a value of the force on. Let's make this slightly easier. Let's say that we have now the following. Let's say we've got a 10 Newton force. So we've got a 10 Newton force. So imagine that this is a sledge. You're pulling a sledge along smooth snow. Let's say that the snow is smooth. Pretend there's no friction. Highly unlikely as there'll always be a little, but we'll pretend it isn't. What we can say is the following. There's no vertical acceleration, so this isn't jumping off the snow, it's not going through the snow. So we can now look and say this is going to be 0 meters per second squared. So if we look at the acceleration in the vertical plane, there's none. Yet we can say now that there might be some acceleration. Let's put some acceleration now in the horizontal plane. And let's say that we have an acceleration of, let's say this is going to be 3 meters per second squared. So again, I'm using very basic numbers, as unrealistic as they might seem, just to make our calculations easy. Okay, let's now resolve upwards. So what we say then is F is equal to ma. The resultant now we're going to find from here, we've got this is 0. So we can say the following. If we consider now the vertical component of this force, the vertical component of this force is now the force acting in this direction. We're going to break this down into basic right angle triangles. So if I had a right angle triangle now, and I had the angle just here, so this angle right here is going to be 30 degrees. I've got now the hypotenuse of this right angle triangle to be 10. I'm interested in now this vertical component right here. So this is going to be 30 degrees. Let's go way back and look at basic trig. We can say SOH. The opposite now, which is going to be the vertical force, is the sine of the angle multiplied by the hypotenuse. So what I can say then, if I look now at the forces acting in the vertical plane, we're going to have the following. We're going to have 10 sine of 30 degrees. So we got 10 sine of 30 degrees. So let's now resolve, and we'll look at the forces acting upwards. This is being pulled upwards. Despite it not seeming that way, if you're walking along pulling a sledge, we've got now a vertical component of that force which is pulling in this direction. We'll have a horizontal component and a vertical. Now I've also got R plus R minus now my 2G, minus the 2G as this is acting now in the opposite direction. So let's see if we can just move this out of the way. So let's go ahead and resolve. So using Newton's second law, I'm considering now resolving upwards. Minus 2G is equal to the mass, which is 2, multiplied now by the acceleration, which is 0. So all I need to do from here is simply work out the value of R. So I can work out the value of R at this stage. So let's go ahead and do that. Let's say now that R will be equal to adding the 2G to both sides and subtracting now the 10 sine 30. Sine of 30 is 1/2, okay? So sine of 30 is 1/2. So this is going to be 10 lots of half, which is going to be 5. So I'm going to subtract that. So that's -5. So we can say that our G is 9.8, so this will be 19.6 minus 5. So we're going to have 14.6 newtons. So that tells me now the normal reaction force is going to be 14.6 newtons. Before, when we had no vertical component of the force right here, we ended up simply saying to ourselves, well, actually, we've got no forces other than these two, therefore the normal reaction will be equal to the weight acting down. Okay, let's now apply another horizontal force. So at the moment we've got this force at an angle and it will have this horizontal component. Let's say I've got now this force, and we will say now that this is going to be some force, some retarding force. And again, generally, as I said, it isn't, let's just call it F, let's call it some force. Now, I've said that this is smooth, we'll just apply some force that's now stopping it moving in the opposite direction. On a rough surface, we could just simply say that would be friction. Let's now look at resolving now parallel to this plane, or in the x direction. What I want to do is consider the horizontal component of this force. So how much of this force is pulling along this way? Let's go back to basic trig. We've got CAH. So if I look now at the adjacent is the cosine of the angle multiplied by the hypotenuse. So if I look here, I've got now 10 cos of 30 degrees. That now considers how much is pulling parallel to the plane. Minus this force F, so minus F, and that will be equal, again, using Newton's second law, to the mass, which is 2, multiplied by the acceleration, which is 3. We can now find the magnitude of this force F by simply solving a basic equation. Now, cosine of 30 is root 3 over 2. Again, you could put that in a calculator. So 10 lots of root 3 over 2 is going to give me 5 root 3 newtons. Minus 6, adding F to both sides. So we can say that F, whatever this is the exact answer, 5 root 3 minus 6 newtons. So that is my answer, and generally in this unit we give our answer to 2 or 3 significant figures. Often it will give you it in the question. I'm just going to leave it as an exact answer. So that tells me now the magnitude of the force opposing the motion, given now that all I'm doing is pulling a sledge along. So that's a force now at an angle. And often students forget to consider the vertical component of its force. So what it's saying is the normal reaction doesn't need to be as strong. If we considered now that this wasn't there, the normal reaction force would be 19.6, it would be 2G. But as we are essentially, if you like, getting some assistance from this force, the normal reaction is reduced. So far we've looked at scenarios where we've got this plane. So we've got some object lying on the ground. Sometimes we might have now a particle, and that might be suspended by a string, okay? So what we might have is something like so. We might have now a string. If we consider T would be a tension in a string. So if I was holding something up, we'd have now the force now in the string pulling up. We'd have the weight acting down. Weight is mass times by gravity. Let's say we had now an acceleration. Let's say we've got this acceleration and I'm pulling it upwards. So if you can imagine now I'm winching something up. And we could say, let's say that this is 2 meters per second squared. Let's say that this is going to be now 5 kilograms. I've got some tension now in my string. I've got the weight acting down. So what we've got here is the following. We've got now 5G newtons. If you like, you can write 5G newtons, or you could write 49. 5 lots of 9.8. So what we've got then, we've got the weight acting down, I've got tension, and I'm pulling up this way, and I'm accelerating now in the positive direction. So what we could use is Newton's second law. Newton's second law, F is equal to ma. So if we now have that, F is equal to ma, we will resolve upwards. So taking the direction of motion to be upwards, we'd have T, the tension, minus now the force acting in the opposite direction, which is minus 5G newtons. That will be equal to the mass times the acceleration. So it's going to be now 5 lots of 2. I can now go ahead and solve and find the value of t. Now, if this was accelerating in the opposite direction, or if you like decelerating, this would be minus, and we'll look at that now. So now I could add the 5g to both sides, so it now be 5g plus now 5 times by 2. So we could factor that if we wanted. T would be equal to 5 lots now of g plus 2. Now g is 9.8, so the tension in my rope would be 9.8 plus 2, which is going to give me 11.8, and then we could go ahead and work out that's going to be 59. So the tension is going to be 59 newtons. So all we've done is considered now the forces acting in this vertical plane. So see this now as something being pulled upwards and something opposing the motion. Say you're losing a battle. Let's say that you were losing a battle now with the weight of an object. So you're hanging over the cliff and you're pulling something. Let's say we have this scenario instead. Let's say we have the weight of someone now pulling downwards and you're pulling back up like so, okay? And we would have now, let's say we've got this now, and say that this is going to be some tension. So let's say that's T. Let's say this person is going to be, let's say that they're 80 kilograms. So that's their mass. Weight is mass times gravity, 80, and this is going to be 80 g newtons. Now let's say that they are going to be going in the direction downwards this time. So what we're going to have is the following. Now I'm pulling back up, they're accelerating downwards. Let's say someone really mean decides to go and push down on their head. Let's say they do that. They might push in that direction. Now we might want to call this, let's say that this is going to be, let's say they apply now a 50 Newton force. So I'm trying to pull this person up. Someone's putting their foot on their head, pushing them down, and they're accelerating, and let's say they're accelerating at 2 meters per second squared. So a highly unrealistic model. Now at this stage, I like to actually model this up and put the force acting in this way. You don't have to, I just think it's nicer to see it like so. So let's consider the following. What we're going to do is find the value of the tension that I'm pulling back with. So we've got this acceleration, we're going in this direction. So what I'm going to do this time is resolve downwards. So if I resolve downwards, and I'll write it just here, we can see now that we've got 80. So this is 80 g. This is the weight, 80 g newtons, plus the 50 newtons, minus now the tension. So the tension is in the opposite direction, and that's going to be equal to the mass times the acceleration. So the mass is going to be 80, and then we're going to have the acceleration. So that's me taking this person to be accelerating downwards with a speed of an acceleration, of 2 meters per second squared. So let's do some rearranging. What are we going to have? We're going to have now on here, we're going to have 80 g plus now 50 minus the 160. And that's just now going to give us some value, and we'll put that in newtons. So if we wanted to calculate this, straight through a calculator, we'd have now 80, so let's do 80 times by g. G is 9.8, that's now the acceleration, and then we would simply add 50 minus 160, which is minus 110. So this gives me now the tension is 674 newtons. So T is 674 newtons. So that's an example of just modelling this up. It won't always be a case that we have these forces given. We might need to find, for example, the acceleration. So let's go ahead and just draw something up. Let's say that I have now some forces acting on this particle. So we've taken it to be a particle. Let's say we've got something like so. Let's say we've got some of these. So let's say that this is going to be a 50 Newton force in this direction. We're going to have a mass, let's say we've got a mass of 20 kilograms, therefore the weight acting down is going to be 20 g newtons. Let's say also I've got a force in this direction of now 10 newtons. So now we might want to find, given that it's accelerating, let's say that it's actually going to be, let's put an acceleration on, let's spin this round, so let's spin this round, and we'll say it's now an acceleration of a meters per second squared. We might need to find a. So here is a meters per second squared. So using Newton's second law, F is equal to ma. If we consider resolving downwards now, we're going to have 10. So 10 newtons plus 20 g newtons minus 50 will be equal to the mass, which is 20, multiplied by the acceleration. So if I consider what this is going to give me 20g, so we're going to have 20g minus now this 40, minus 40 will be equal to 20 lots of acceleration. So this time now I'm solving for the acceleration. So if I divide both sides now by 20, we're going to have g minus 2 is equal to the acceleration. So g is 9.8, 9.8 minus 2, 7.8 meters per second squared, and that's going to be fairly uncomfortable. So there we go, that is the acceleration. Again, wildly inaccurate models lots of the time, but this might be something that we see. So in this case, all I've done is gone ahead and solved now for the acceleration. You might need to solve for the mass. So for example, if we had a scenario, let's do another scenario. Let's say we've got now this, so say we've got some forces acting on. Let's say that we've got now the weight acting downwards. So we've got the weight acting downwards, we've got a force. Let's put a 20 Newton force on this, and we might say that this is going to be accelerating up. Let's go for 2 meters per second. So let's put on here now, this is going to be m. Okay, so let's say we want to find m. Let's say we're going upwards with an acceleration of 2 meters per second. So 2 meters per second squared. Say we've got a 20 Newton force, and then now we've got mg, the weight acting downwards. We might want to find now the value of m. So using Newton's second law, if we consider F is equal to ma, all we would do is go ahead and resolve upwards. So we could say the following. Going upwards, we're going to have now 20 minus the force mg will be equal now to the mass times the acceleration. The mass is 2, the mass is m, the acceleration is 2. So we got to 2m. So let's just rearrange this. We can say 20 will be equal to 2m plus now mg. So factoring the m out, we can say 20 is equal to m, then we've got now g plus 2. G plus 2, 9.8 plus 2 is going to be 11.8. So we could say that the mass would be 20 over 11.8. And again, that would be kilograms, and you could find that from there. So as you can see, lots of these basic problems we can just go ahead and solve for. Everything that we've looked at in this video has been fairly basic. It's just considering forces acting on a particle. The force might be a frictional force if we've got a rough surface, and the frictional force at opposed motion. It might be a pushing force, which we call a thrust. It might be a pulling force. You might even be given now, it's just simply a force retarding the motion. If you're given, for example, a pulling force, that would be seen as the tension, and we can simply model that up as T. In later videos, we're going to look at more problematic scenarios and where we've got more to deal with. But hopefully this has given you a good idea of working with basic forces. So let's just finish now with a couple. We'll just have a couple of slightly more challenging ones. Let's say we've got this scenario. So let's say I put now this is a box, and we have now, let's say we've got now a force. Let's say a force, and this is going to be pulling at an angle now. So we could say now that this is going to be tension. So let's model tension up, and we'll model tension up. Let's make it quite a big angle. So let's say that that is now going to be, let's say that this is going to be, let's go for now 60 degrees. Let's say this is 60 degrees. Okay, and let's say this is going to be 20 newtons. Let's say we've got now a mass of 10. We're going to have now a weight acting downwards. So let's have now the weight acting downwards. So let's go ahead and do that, and then put a normal reaction. So normal reaction is going to be perpendicular to this plane. Now let's put on a different force. Let's say we've got two kids who have tied this box now, and one is going to be pulling in this direction, the other will be pulling in this direction. So let's look at an angle, and let's put this angle on right here. Okay, so what we've got, let's say now that we've got, let's say that this is going to be T. Okay, let's say this is T, let's say this is going to be R, and let's say now that this is going to be an angle. I appreciate it's not accurate, but that's 30 degrees. So we'll be told now that there's no vertical acceleration. So this box or whatever they're pulling is not jumping up and down off the ground, it's just now 0. And it's highly unlikely that you would see this as 0, but we've got no now acceleration in the vertical plane. Let's say we've got an acceleration in the horizontal plane, and let's say that it's going to be in this direction right here. And we could say that this is going to be, let's make this nice and easy, let's say it's 2 meters per second squared. Okay, so the weight acting down is going to be 10 G newtons. So this is what we call a force diagram. You can actually take this out and just have the triangles. Often I like to just do it like so. So let's just draw this up. With the particle now, I just like to draw the arrow. So if we looked at it now, we'd have this one in this direction, this one in this direction, and then we would have now this one right here. So let's spin this round, placing that like so. So let's put that there, we'd have that. So if you just really wanted to slim this down and look at all of the forces acting on the particle, we could simply do this, okay? So we'd have something that looks like that, and then we could put our acceleration on. Over time, you might want to simplify the model to give you this. So if we just look at it, this is going to be 10G. So 10G, we've got now 20, we've got T, we've got now an angle, and you might often see this as the angle of 60 and this of 30. Just to make you aware of that, 30, we've got now 60, and then we've got this normal reaction force. Normal reaction force perpendicular, and then we've got 2 meters per second squared. Okay, let's go ahead now and resolve upwards. If I resolve upwards now, I'm going to get an equation for R and T. So resolving upwards, what we can do is the following. We can say now, and we'll take up to be the positive direction right here, we can say R plus now the vertical component of this force. Now if I break this down into vertical and horizontal components, the vertical is going to be T sine of 30 degrees. So plus T sine of 30 degrees minus now the 10G plus this force right here. So minus the 10G plus, and I think in fact I'll write it, let's write the pluses first, let's keep, it's just better convention to do this. Plus now 20 sine of 60 degrees minus 10G will be equal to the mass times acceleration, which is going to be 0. So if we look at this now, I've got R plus the sine of 30 degrees is 1/2. We've got 1/2 T. The sine of 60 degrees is root 3 over 2. Plus now we're going to have, so that's just going to give me 10 root 3 minus 10G is equal to 0. So what I've got now is an equation for or in R and T. So I could express now R in terms of T. So what we could say then is R would be equal to now 10, and if I wanted to I could say 10G minus 10 root 3, or I could say 10G minus root 3 minus now 1/2 T. So minus 1/2 T. So I've expressed R in terms of T. You can do it any way round. You could even at this stage multiply by 2. You could say 2R is equal to 20 lots of G minus root 3 minus T. So that's now 2R in terms of T, or you could have T in terms of R. This is entirely up to you. As you can see at the moment we have 2 unknowns. If I go ahead and resolve now parallel to the plane, if you like, or in the direction from left to right, let's consider these. What we've got now is the following. I've got here that this particular force is going to be now 20 cos. So I'm looking now at the horizontal component of this force. So 20 cos now of 60 degrees minus this force right here. These are the only 2 forces acting in the horizontal plane, minus T cos of 30 degrees must be equal to the mass, which is 10, multiplied by the acceleration, which is 2. So it's with this, we can see now that we're going to get a value of T. So I can get a value of T and simply sub it back in this one to get R. So if you like, do this one first, knowing now that the only unknown in the horizontal direction is T. If I want R, I need T, but essentially we can get T straight away. So what we've got then is the following. Cos of 60 degrees is 1/2. Again, if you want to check this on a calculator, I'm using now the exact values. I'm using nice angles. But if we put that in, we get 1/2. If we times it by 10 or whatever it was, by 20, we're going to have now 10. So what we've got then is 10 minus t cos of 30. Cos of 30 is root 3 over 2. So we've got t root 3 over 2 or root 3t over 2. And that's going to be equal now to 20. Okay, so if we look at this now, what we're going to have is the following. We're going to have that t, let's put this in, if I add that to both sides, we can see that minus 10 is equal to t root 3 over 2. So if we wanted, let's just do that, let's divide both sides by root 3 over 2. We could say now that minus 10 over root 3 over 2 is equal now minus 10 over root 3 over 2. So that's going to be minus 20 root 3 over 3 is equal to t. So if you were asked now for the magnitude of that force, it's just 20 root 3 over 3 newtons. All I've done is just rationalise this. If you put that in a calculator, let's go ahead and do that. So let's say we had minus 10, no, don't want to do that. Let's grab that up. So we had minus 10 over now root 3 over 2. Let's put that in. All I've done is simply rationalise that from there, and that's going to give us that. Okay, so that's just telling me now that this force, this t, is 20 root 3 over 3. So instead of having t, we could say now that this is going to be 20 root 3 over 3. The reason it's come up to be negative is that I've taken the positive direction to be from left to right. So if we look now, we can find r by simply subbing it in here. I know the value of t. I know that the tension now is going to be 20 root 3 over 3 newtons. I might want to find the normal reaction. So what I can say then is 2r will be equal to 20. Then we're going to have g minus root 3. And then I'm going to add this in. So it's minus minus. So we could say plus now 20 root 3 over 3. And this will give us the normal reaction. So we could say the normal reaction, if we divide both sides by 2, is going to be 10 lots of g minus root 3 plus now 10 root 3 over 3. And whatever that comes out to be in newtons, that will be now the normal reaction. So in this particular case, I found two unknowns simply by using essentially simultaneous equations. We could have gone ahead and now resolved horizontal, or looked now going from left to right and found the value of t. Then subbed it in here. I went up and down first. In hindsight, or with hindsight, probably better to get t first, just for your own peace of mind. It really doesn't matter, as we needed r, which was now dependent on having t, and then we subbed it in. So that's a slightly harder example where we've got a diagram showing the forces and we need to resolve parallel and perpendicular to the plane to find these. Okay, I think that's about enough for now, because I've kind of been making these up as I go. In the next video, I think we will look at the force. So forces such as frictional force acting on a particle. But for now, hopefully that's given you a good idea of now resolving forces. So it might be tension, it might be thrust, it might be friction, it might be the normal reaction. These are all forces that could act on a particle and alter its speed.